Sigma rules, pySigma, and detection engineering. If you think those three things are just about writing search queries, you're already behind the attacker. Let me take you back to December 10th, 2021. Log4Shell drops. Within hours, attackers were scanning the entire internet with a string shorter than a tweet. And inside enterprise SOCs, everywhere, analysts were all trying to write the same detection 3, 4, 5 times over. Once in Splunk SPL, once in Sentinel KQL, once in Elastic DSL, because none of their tools spoke the same language. Now this isn't a tooling problem. It's a structural failure in how the industry builds detection. Sigma exists because of it. Here's the ground we'll cover today. The history of detection engineering and why every paradigm before Sigma left a gap that attackers learned to walk straight through. The real architecture of production Sigma rules, modifiers, and correlation specs included. Then the pySigma toolchain that actually does the translation, and the failure modes nobody puts in the tutorial. Most teams pull Sigma rules off a public repository, run them through a backend converter, push them to their SIM, and call it detection engineering. They never test against real malicious logs. No positive samples, no false positive baselines, just a simple syntax check and a deploy. And that is not good enough. That isn't a detection, it is security theatre with a YAML file as the prop. And here's the part that should bother you. In a fresh deployment, the overwhelming majority of your false positives won't come from bad threat intelligence or broken logic. They'll come from missing filters and field mappings nobody documented. By the end of this video, you'll know exactly where that comes from and, more importantly, what to do about it. Detection engineering has a clean, evolutionary arc, and every paradigm has emerged because the last one had a blind spot that somebody learned to exploit. 1995, Zeek, back when it was called Bro, the first serious attempt at network level behavioral analysis, protocol state tracking, connection anomalies, watching packets cross a boundary. 1998, Snort, this is the one that democratized detection. Open rule sets, port matching, payload string signatures. For the first time, community written rules could be shared and deployed. The architecture shaped everything that came after it. 2010, Suricata. It fixed what Snort couldn't, scale. Multi-threaded deep packet inspection at that enterprise speed. Faster, better, same fundamental blind spot. Here's the blind spot all three share. They watch the border. The moment an attacker is already inside, moving laterally, escalating privileges, pulling credentials out of memory, these tools see nothing. No suspicious packets, no malicious payload, because the attacker isn't carrying one. They're using PowerShell, WMI, PSExec, tools your organization trusts, living off the land. 2013, YARA. This moved the detection surface off the network and onto the endpoint. Pattern matching against binaries on disk, hex bytes, string signatures inside file structures. A real shift for detection engineering. But YARA has its own structural ceiling. It's scanning files or memory dumps. An attacker who uses legitimate tools, living off the land, gives YARA nothing to scan. The file it's looking for doesn't exist. 2017, Sigma targets system and application log telemetry. It doesn't care what's on disk. It watches what the system does. Parent-child process chains, command line flag combinations, network socket allocations, and administrative share connections. The contrast makes the gap obvious. YARA, does the byte sequence exist in this file? Sigma asks, did this sequence of events happen inside a running system? That's the paradigm shift. And Sigma does something no standard has attempted before. It is platform agnostic. One YAML file, one piece of detection logic, compiled into whatever query language your sim happens to speak. That is the idea that Florian Roth built Sigma around. A universal language. The rule is the plug, your sim is the wall socket, and pySigma is the adapter you slot between them. When Log4Shell dropped, Roth published a rule to his GitHub. SOC analysts around the world ran their translators and had working detections across completely different sim backends within a matter of minutes. That is the operational case, made in one incident. The architectural case runs a bit deeper. Writing a Sigma rule and deploying a Sigma rule are two completely different engineering problems. A valid Sigma rule organizes its top-level fields into three functional layers. Layer 1 is metadata, the operational context. Every rule carries a unique UUID token, so it's globally unique across a library of hundreds. A status field tracks maturity from experimental through test to stable and finally deprecated. Severity runs from informational to critical. And the tags block cross-maps the rule into MITRE ATT&CK, so a rule on exploitation attempts ties straight into attack T1190 inside your sim's taxonomy. That mapping isn't just decoration. Automated pipelines read those tags to populate attack heat maps. Layer 2 is log source, and this is where the performance lives. Three attributes. Category defines the logical event group, like process creation, network connection, web server. Product isolates the platform, Windows, Linux, macOS, and service selects the precise log channel, like Sysmon, security, PowerShell, SSHD, or Okta. Scope it tight, and the backend only touches the data it needs to touch. Leave it broad, and your rule will sweep the entire store on every single evaluation. There's also an optional definition attribute that carries deployment advice, telling you whether your endpoints are even configured to capture this telemetry. A process creation rule is useless if command line audit policy isn't switched on. That's a detection gap you will not see on your SIM dashboard. Layer 3 is the detection block, where the logic actually lives. Runs on one rule you have to memorize. YAML lists are logical ORs, and YAML dictionaries are logical ANDs. A dictionary needs every key value pair to match at least once. A list fires if any single value in it appears. The condition statement at the bottom is the Boolean glue, combining your selections with and, or, not, parentheses, and shortcuts like one of selection star or all of them. The production design pattern behind most real-world rules is simple. Select the bad, filter out the good. Selection and not filter. You isolate the malicious behavior and then just subtract the legitimate admin activity that would otherwise drown you in false positives. Modifiers are where Sigma earns its resilience. You append them to a field with a pipe delimiter and they change how the value gets evaluated. Contains wraps a string in wildcards so it matches anywhere in the field. Starts with and ends with anchor to the front or back, so ends with cmd.exe won't fire on a binary that just happens to contain that string mid-path. All flips a list from OR to a strict AND. Every item has to appear, which makes it precise for order agnostic flag checks. CIDR matches IP fields against subnet notation. Windash maps the Windows flag prefix variants, so you get a match regardless of which one is used. They do include an RE modifier that hands the value to our regex engine. Keep that one in your back pocket though, because it is quite draining on performance. So how does the YAML actually become a query? That is where pySigma comes in. The architecture is deliberately modular. Core library stays slim. A YAML parser, the Boolean logic handler, and the modifier evaluator. Everything platform specific lives in separate, decoupled plugin packages. One plugin per backend, one per pipeline. Each vendor maintains their own, so Splunk can ship a backend updates without anyone touching the Elastic plugin. It works in 2 layers. First, the processing pipeline will normalize field names, because a generic field like image has to become process.executable in Elastic Common Schema, without rewriting the rule for every detection. Then the backend compiler turns the normalized Boolean logic into native query syntax, SBL for Splunk, KQL for Sentinel, ESQL or Lucene for Elastic. The -t operator picks the backend compiler. The -p flag applies the sysmon field mapping pipeline. The trailing path converts an entire folder of rules in one pass. And that is the production workflow. You have the backend, you have the pipeline, you have the rule set. Remember, pySigma is a powerful abstraction, but not a magic translator. The further your environment drifts from a standard ECS or Windows schema, the more pipeline engineering you own, the more customization you need to add in to the backend to make it all work. Everything so far is a single event detection. One rule, one log entry, one match. But a huge slice of real attacker behavior, brute force sequences, privilege escalation chains, multi-stage exploits, can't be modeled by a single event rule. You'd have to fire on each stage and correlate it by hand, or rely on your sim to do this. That was true right up until Sigma version 2 came out, and most analysts still aren't running or making use of the full capabilities that Sigma version 2 provides. Let's take a look. Sigma version 2 correlation rules are the answer to that single event limit. They're separate meta documents that reference your base rules by name and define conditions across multiple events. 4 models in the spec. We have event count, which fires when a base rule triggers more than n times in a window. 10 failed logins in 5 minutes, classic brute force. Then we have value count, which watches the number of unique values in a field. Failed logins hitting more than 100 distinct usernames from one source? Well, that's password spraying. Not 100 attempts, 100 different targets. That distinction is the signal. Temporal fires when several different base rules trigger inside a time frame in any order. Good for a toolkit that drops multiple indicators at once. Then temporal ordered fires only when base rules trigger in a strict designated sequence, say an inbound web exploit, then a suspicious child process. That's your exploit chain detector. A standard Mimikatz rule fires on a single LSS handle event. So I rename the binary, run it from a trusted process, and stage it across 3 machines over 6 hours. Every event on its own just looks like noise. Nothing trips. A temporal ordered correlation rule chains it together. Suspicious LSS access, followed by credentials in registry, followed by lateral tool transfer, all inside a 30-minute window. The sequence that looked like noise, event by event, becomes a confirmed TTP chain at the correlation layer. The version 2 spec deliberately targets the most common correlation patterns, count, sum and sequence, to keep rules portable across SIMs. Any backend that can't support a given correlation type is required to throw a clear compilation error, not a silent failure, not a broken query that deploys clean and never fires, but a hard stop. In detection infrastructure, a loud failure you can see beats a silent one you can't every time. But hold your horses before you go out there and start shooting off Sigma rules left, right and centre. Sigma is great, but there is a production reality that most tutorials skip. Generic Sigma rules are broad by design because they're built to survive in environments they've never seen. In yours, that breadth will cost you. The bulk of false positives in fresh deployment trace back to 2 things: missing exclusion filters and field mappings nobody is documented. The rule expects telemetry your endpoints might not be generating. The field names might not match your schema. The severity might not match your escalation policy. One more, on the plugin ecosystem itself, the decoupled vendor maintained backend design is generally good engineering, but quality across those backends is uneven. Splunk and Elastic are mature. Others have undocumented field gaps, missing modifier support, and no maintenance guarantees. So before you build a pipeline that depends on one of those backends, the answer to "does this handle my rules?" is not the README. It is a CI run against your actual rule library and testing before deploying. Here's what this video deliberately left out. Everything we covered, Sigma, pySigma, detection as code, is the craft of building and shipping a detection. None of it is the discipline that decides what to build in the first place, proves it works against a real adversary behavior, and keeps it honest over time. That discipline is detection engineering. It starts with requirements. What are you actually trying to catch and why? It then moves through prioritization against the threats relevant to your environment, into building, then validation against emulated adversary behavior, and then measuring your coverage against a framework like MITRE ATT&CK. Sigma is one tool inside that loop. It is not the entire loop. This video walks you through that life cycle end to end. By the end of it, your Sigma library stops being a folder of things you found on the internet and becomes the output of a process. That's the difference between writing rules and detection engineering. Like and subscribe if you want more deep dives into everything cyber threat intelligence, detection engineering, and threat hunting. See you in the next one.